Yeah, so we set up the motivation in the previous class in terms of why composites. So we're going to answer a few more questions that we set up last time, like so this is already done in the previous class, so we'll start off today with what, so that then we'll get on to, and as you know, this is the kind of crux of the whole course in terms of structural analysis. So whatever we've been doing so far is essentially trying to get to the motivation in order to do that. The motivation that we set up is also just like all structures, it's of two parts: motivation for the geometry, motivation for the material, right? So motivation for the geometry we already finished in terms of why shells and beams and why semi-monocoque constructions come bringing shells and beams together, and individual components, what they are called based on the geometric aspects and what is the main function that they perform. Now we have set up also the same kind of motivational question for geometry, what we did for the material as well, and based on that we said certain alloys, and better than that, superior than that for most applications, the composites, right? So we kind of understand their limitations, because we said in spite of these issues we are still going with them because we know how to handle some of those limitations and overcome them. And more importantly, the advantages far outweigh the disadvantages. Now we need to formally look at what composites are, and essentially they are mixtures, right? But they're a specific kind of mixture because the alloys are also mixtures, but a mixture of a different kind. And the main difference comes in terms of the interface between the multiple constituents or the materials that make up the composite, that the constituents are typically distinct at a macro scale rather than at a micro scale, right? So again, macro and micro are kind of relative terminology, but still we kind of understand that. So mostly it's at the visible level you can distinctly see where the fiber ends and where the matrix begins and where the next fiber starts. So more importantly, they are chemically distinct components and they are not kind of chemically reacting with each other. So that's one of the compatibility requirements. There are many compatibility requirements between the choice of the fiber and the choice of the matrix, and one of them is that of course they shouldn't be reacting with each other, right? So we see that in terms of the actual choice of the constituent, whether it's for the fiber or it's for the matrix, can come from three primary structural material categories. The first is metals, the second is polymers, and third is ceramics. So these kind of have driven throughout the history of humanity, both in terms of nature-made structures as well as engineered synthetic structures. It's essentially from one of these three categories that people have chosen, but nature for a long time has showed us that individually each one of them may not be that good for a lot of applications, so you need to kind of combine them, and they need not be combinations from multiple classes. Within a class there are so many members of each of these three classes, so you could probably be combining between them as well. So there are, for example, polymer fibers in polymer matrices, etc. So there are various possibilities that are there, and one of the most high performing composites, especially for space applications and also re-entry vehicles, is the carbon-carbon composite. So essentially it's a ceramic matrix in a ceramic fiber in a ceramic matrix. So the idea is, unlike other mixtures, this has distinct interfaces, but at the same time the interface is strong enough that it doesn't so easily break away in the typical kind of a loading situation, unless it is stressed beyond a certain value, which may be well within the design realm that you have in terms of the VN diagrams that we talked about. So that is very, very important. So while mixtures are quite common, they're the specific kind of mixture that we're talking about here. One, it has distinct interfaces and the bonding at the interface is fairly strong. And the most popular amongst them are the fiber reinforced composites, but that's not the only kind of composites. There are particulate composites where you have particles like, let's say, carbon nanotubes, etc., which are within matrix. So very similar in terms of how the overall analysis is done, but just that the possibilities are numerous. But what has kind of stood the test of time for a long period of time, not just in the aerospace industry, but many spin-off industries as well, is in terms of the fiber reinforced composite. So now we are at a stage where we see that yes, there might be additives, but the primary two members are your fiber and the matrix. The fiber has its own functions, the matrix has its own functions. So while in the end of previous class we discussed why composites, now we need to look at these two major constituents, the fiber and the matrix, and say why fiber, why matrix. Okay, so that's essentially what will kind of occupy most of today's class, at least the first half. So that's essentially what we are looking at. So, and why is this particular type of composite, that is where the reinforcement is in the form of a fiber geometry, what is so special about a fiber's geometry that it has become so popular? Obviously it's become popular because it has certain advantages over the other geometries, other kind of form factors, which has made it so much more relevant for a high demanding application like aerospace. So what is it so specific about fiber's geometry is what we would like to explore to start with, right? So before we head to that, in terms of the geometry of the fiber, let's see what are the typical candidates that you have. Let me start with a motivational example of something that is kind of the state of the art, at least was the state of the art a couple of years ago at least. So in terms of the largest value of Young's modulus that you can have amongst most typical materials that are readily available for use. This is a name of a company, Toray, so it makes carbon fibers. So obviously it's commercially available for anyone to buy. And another from the same manufacturer, which has a very large ultimate tensile strength. So it's kind of a trade-off. See, because if you have very large Young's modulus, then you have only a UTS of 3.82 gigapascals, whereas you can go all the way up to 7 gigapascals in one case. So the 2% that I'm talking about is the percentage elongation. Like here it's 0.7%, it's 2% over there, right? So sometimes it's an advantage to have larger elongations because especially in impact kind of applications, because it absorbs more energy, because the area under your stress strain curve is a measure of how much energy can be absorbed per unit volume of a material, right? So for such applications we prefer large elongations, but in applications where you're looking at the deflections being very, very small, contained within a very small window, then you would like to see that you want that to be small. But essentially you're looking at a trade-off here between these two materials, these two candidate materials, between Young's modulus and ultimate tensile strength. If you want very high ultimate tensile strength, you have to live with a reasonably low, comparatively speaking, at least in terms of the Young's modulus, for 324 instead of 588 GPa. So that's essentially the kind of trade-off that you have to be looking at. The very fact that we are stating UTS in GPa is by itself very special, because rarely is it put in GPa. It's mostly given in MPa, because in GPa it might be a very, very small number, it might not look good to put it in numbers. So we typically give this in MPa, but these have such large values of UTS that we are putting in not only E in GPa but also UTS not in MPa but in GPa. Now this is as far as some of the cutting edge fibers are concerned, but as I said, this data is about 2 or 3 years old, so you might have much better fibers that have come out beyond this as well. May or may not have commercial availability, but there are fibers. And one of the best kind of fibers that you have are what are known as whiskers. Whiskers are also used for the mustache, but essentially you're talking about the thinness that you can get to in terms of a fiber geometry, the diameters, and that's essentially what would be In some cases they might be much more than this, but the problem with them is they are available in very, very short lengths, whereas these can be made in much larger lengths, especially for filament winding, etc. That might be a requirement, right? So this is one end of the spectrum. The other end of the spectrum, which is more commonly used in the aerospace industry, but also in other industries as well, are the run-of-the-mill kind of composites that you have. We're only talking of fiber properties, remember here, and you cannot use fiber by itself, okay? And we'll see the reasons. You might already be aware of some of those reasons. We will see some of the main reasons why you can't use fibers by itself. So this might be a little more attractive than what it really is, because obviously you're not going to use it as it is. You're going to use it with a matrix which is much lower in E and UTS, and the end composite that you're going to have will have much lower than this, but still will be of the same order of magnitude, which is what is important for us, right? So now coming to what is more commonly used in the aerospace industry, you typically have some of these carbon fibers getting into an epoxy matrix, and you see that in GPA, if you look at the kind of properties that they have, the Young's modulus is of the order of 240 to 360, whereas which is in GPA. So this is the Young's modulus that we are talking about, whereas here we talked about as high as 588. So this is what is kind of a rare situation, because these might be much more expensive typically compared to those, and for most applications that might be good enough. You might not want to go for the current state of the art or whatever, especially if it's a large scale application, then it becomes very difficult to wield with this. Right. Then also in terms of the availability, because of certain geopolitical situations, etc., it may not be available all around the world. It might be restricted to certain nations, etc., if it's for cutting edge applications, especially in the defense areas, etc. Right. And we also saw the case of boron in the previous thing. You can see that it's fairly high in terms of the Young's modulus. So a lot of space applications for antennas, radars, etc., where the deflections are of a big concern. So you want deflections to be as minimal as possible, which means the stiffness has to be more, flexibility will be lesser, and therefore you typically go for that kind of fibers over there. But yeah, amongst all that are listed over here, you could see probably this is the largest of the E. On the other hand, if you're looking at in terms of the sigma U, the ultimate tensile strength, you're looking at 3.6, a carbon fiber, a specific kind of carbon fiber. Just like Toray was a company which is listed here as well. There is another company called Hercules, which is also a very large manufacturer of carbon fibers, and they have their own grades in terms of what they are made out of. This all depends on the precursor that is used to get to the carbon fiber. Like for example, they could use polyacrylonitrile, PAN as it is called, and based on what precursor they start with, some might end up as very large Young's moduli kind of fibers, or they might instead end up as very large strength kind of fibers with lower Young's modulus that you will have to deal with. So it's essentially a trade-off between the two. And these last two are very important in a lot of applications where impact is of concern, like for example the engine housing, etc. There the aramid fiber, aramid is the chemical name I mentioned in the previous class also, in terms of the commercially available name from DuPont, which is called as Kevlar. Again, within them there are many gradations, of which two are very popular, the Kevlar 29 and Kevlar 49. As you can see, Kevlar 49 is superior in terms of the Young's moduli. As far as the tensile strength is concerned, they are pretty much the same, right? So the larger Young's modulus essentially means that you have a steeper stress strain curve, but going up to the same value of sigma u. But what is important is also where it breaks off. Typically these being polymer kind of fibers, they will not have as brittle a fracture as some of the other fibers that are listed over here. So in other words, boron, carbon, etc. will suddenly break, whereas these will elongate a little more before they break, which is why they can absorb a lot more energy, because if they are going to fail at a much larger elongation, it means there's much more area under the stress strain curve. So that's essentially what you're looking at there. Then of course for cost sensitive applications, typically low performance aircraft or aircraft which are made in a bulk manner, very large numbers. So they typically will go for glass fibers, and within glass fibers again there are many categories. Two very common ones are E glass and S glass. E stands for electric and S stands for structural. So the structural one is what is more commonly used, because you can see very clearly the Young's modulus and the ultimate tensile strength for the S glass are much larger than, not much larger, but larger definitely than the E glass, especially the ultimate tensile strength is larger by a bigger margin, right? Now, as far as densities are concerned, they're pretty much the same within a particular category. So if you look at S glass and E glass, they're within relative densities about between 2.54 and 2.48. Relative density, as you know, is a non-dimensional number, which is also the same number as far as gram by cc unit of rho is concerned, because the comparison is with water, and water has a density of 1 gram per cc, so which means that you divide by 1, and therefore the relative density is what you're talking about. So the range is very, very small between different kinds of glass. Similarly, if you look at the 3 carbons, you see that it's on top of each other at least up to 2 decimal places. It's pretty much the same. It's only in E and sigma U that you could have much more variation, because chemically it is the same. It's just how the atoms are getting arranged relative to each other, which makes these properties quite different from each other, but the mass for a unit volume remains pretty much the same. And boron, as I said, involves a carbon fiber with a boron coating, which makes it a little heavier because it's much thicker, and boron typically has density which is larger compared to the carbon fibers. And then of course Kevlar, the densities are much lower than even glass for that matter, and but it's kind of niche applications of where energy absorption is the criteria. You could also see in the case of racing cars, for example, for used in Formula 1 kind of applications, where the crash guard is essentially could be made out of Kevlar kind of composites, right? So these are mechanical properties of a few high performance fibers. Now the question is, what does this high performance typically mean? So though it's a subjective adjective, high performance, what you call as high performance or low performance, and this also evolves over time as materials develop. What was high performance yesterday could become low performance today because of new developments in materials. But nonetheless, there's a basic or rather very fundamental classification which is typically done in terms of fibers, what are called as basic fibers and advanced fibers. So basic fibers, and there's a kind of a thumb rule which is followed in the industry, both in the composites materials industry as well as in the aerospace industry. We say that anything which is having a Young's moduli in tension of along the fiber direction, of course, which is less than 100 GPa, you typically call them as low modulus or basic fibers, and these are typically much easier to make, or made out of raw materials which are much easier to obtain, and therefore typically the cost is much lesser for basic, and therefore you will find a lot of these applied not only in aerospace but also in non-aerospace applications, which are much more cost sensitive than the aerospace industry. So that's precisely what I said, economical high volume applications. So where you have to manufacture a lot of the same vehicle, for example, which might be large vehicle, and you require a lot of this particular material, then the amount of investment overall absolute is much larger, and therefore it will make a huge difference whether you use such basic fibers or a more advanced fiber. So some examples of such basic fibers which have a low modulus, less than about 100 GPa. You see in this table itself, you can see there is Kevlar 29. In addition, you also have these two, the glasses S and E. So all three of them are having Young's moduli less than 100, right, GPa. So some classic examples of application are not in the racing automotives, but in the regular passenger automotives, which are made in much larger numbers, and therefore the cost is it's a cost sensitive market, and therefore you go for such lower cost fibers. So that's the main advantage, low cost. So the other category is obviously if one is less than 100 GPa, the other is greater than 100 GPa. There's nothing hard and fast about 100 GPa. It's just a thumb rule, as I said. So there can be materials which lie at the interface, which can go either way. For example, S-glass is fairly close to Young's moduli of about 100. So for all, you can pass it on as a advanced fiber, and in fact many aerospace applications, especially helicopters, etc., use a lot of this S-glass, and I think you brought out some of those examples as well in one of your homeworks already. So what is the issue with the advanced fibers? Yes, they are high modulus, which is very great, but they are expensive, and some examples of that are the typical carbon fibers and also Kevlar fibers. Even though Kevlar 29 has a very low GPa, it is something that will have a large elongation before it fails, and as I said, is good at impact kind of applications where impact is a dominant load, and therefore it's also quite expensive to make such aramid fibers. But of course Kevlar 49 is even more expensive compared to Kevlar 29. Therefore relatively speaking, you have more exotic applications, aerospace of course, in addition sports. So especially high performance sports like tennis rackets, golf clubs, you could have various other kinds of applications where performance, the whole idea is even a little bit of performance gain, I'm willing to pay more money. So that's essentially what a sportsman would do or a sports team would do. And similarly for aerospace applications, a small gain in performance could accumulate in terms of market value for the customer, let's say an airline which is running that. If there is, let's say, much better fuel efficiency, the specific fuel consumption comes down, SFC, then you have a huge advantage. So what you spend on the initial cost in terms of manufacturing because of the material, you might be reaping back the benefits in terms of the life cycle costs of the entire vehicle in terms of running it over a long period of time, typically 20 years, 25 years, etc. Right? So this is precisely what I stated, that the performance has to justify the cost. The increase in performance rather has to justify the increase in cost. So once that happens, you are willing to move from a basic fiber to an advanced fiber, which is available in lesser quantities, and therefore more expensive, because the supply demand aspects of economics come into play over here, right? So now, just like in the steels, we had some kind of an understanding in terms of the state of the art. Here, this is not the state of the art, I would say, but an overall understanding of different kinds of materials. So you have various kinds of materials over there. So you would see that, for example, let's start with the lowest end in the chain, foams. Foams are typically not great structural materials, but they might be filling materials. For example, we introduced, when we are talking about the stiffness based design, a sandwich construction, where we said the intermediate layer, the core, could be made either out of aluminum honeycomb or such foams. Okay, various kinds of foams are there. There are metallic foams as well, which are typically better compared to foams which are of the run-of-the-mill kind, typically polymer-based foams. But you have, this is what we're talking about, rigid polymer foams, MD, and so on. So it's a wide range. And even before that, you should see that we are plotting absolute values here. It's not like something which is tailored for aerospace engineering, where specific values are more important. In fact, we already derived the metrics or the performance indices for strength-based design and the stiffness-based design, where we were saying that this divided by rho, the material mass density, is what is of concern to me. Similarly, the square root of this divided by the mass density as the square root of the whole thing, the ratio, is what we were interested in there from the specific point of view. But here this is an absolute chart for all kinds of applications, not necessarily weight sensitive applications like in aerospace engineering, and there you can see the wide spread of materials that are there. So this green chunk of materials are the foam kind of materials. So, and it's a log plot. You could see that here you are going from 0.1, 10 power minus 1, 10 power 0, 10 power 1, 10 power 2, 3, etc., 10 power 4. Similarly, over there also you see it's in powers of 10. So it's essentially a double log plot. Okay, both the x and the y axis are logarithms of the tensile strength and the Young's moduli respectively in GPA, MPa and GPa, right, respectively. Now there are certain curves that you see over here, because this is a log plot. Depending on the powers that are of interest over here, compared to sigma t, which is the notation for the tensile strength, and E, which is the notation for the Young's modulus, you see these lines over here, sigma t by E, sigma t squared by E, sigma t power 3 by 2 by E. Some of these ratios become kind of important, and you see that there are two extremes where you know that all structures can fail in two ways generally. One is material failure, the other is geometric or elastic failure by buckling instability, right? So if you go above this line, you are essentially looking at material failure, that is yield, for example, occurring before elastic buckling or essentially instability kind of failure. On the other hand, if you go below this over here, you are looking at buckling being of bigger concern than yield. So because you have such a large tensile strength already, it's very rare that you would have a failure coming because of the material giving up, that is yielding. On the other hand, here the tensile strengths are so low that it's very clear that it might yield well before it buckles. So that's essentially what we are talking about. So all these lines that we are seeing are essentially those kinds of lines, and typically lines which are parallel to this that you see over here, here and here, those are all, as you can see, sigma t by E equal to a constant. So larger values of sigma t by E that we are looking at. So essentially that we are looking at over there. Now let's look at the other chunks. We already looked at foams. Then typically you have what are known as non-technical ceramics. So it means that are typically not used in the engineering industry a lot, except for example civil engineering, for example. It's one end of the spectrum, but most of them are non-technical kind of ceramics where it's not kind of very large loads that are coming in, but you do not want too much of deflections taking place. So you are looking at giving more importance to it being almost rigid rather than capable of taking too high a load, right? Then on the other hand, you have slightly better than the foams as far as the tensile strength are concerned are the elastomers. So this is one category of materials. Elastomers kind of quite commonly used, especially in joints. When you are want high level of flexibility at joints, all kinds of joints, revolute joints, hinge joints, etc. Many cases you will see elastomers being applied. Typically they are kind of hyperelastic materials, so the Young's modulus that you have might be low, but essentially they are going for very large elongation. Elongation is not something that we can read out of this plot because that's not specifically plotted over here, but that's one of the advantages they have. But they are essentially having greater tensile strength compared to the foams. Then we go, the more we go away from the origin over here diagonally, the better from both points of view, from a stiffness point of view and from a strength point of view. And therefore what lies closest to the top right corner of this plot is probably the best. And there you have metals and alloys. Not surprising, because we are plotting absolute values here. We're not plotting divided by density. The specific values is not what we are plotting. So metals and alloys kind of rule the roost. So non-weight sensitive designs, they are the best. But then weight sensitive designs, we need lower density materials as well. But density is also not factored into this plot, as I already said. And therefore composites are you see CFRP, epoxy matrix kind of composites are all within this. And many of them are comparative in terms of some of the high performing metallic alloys like titanium alloys, etc., as far as the absolute values of tensile strength and Young's moduli are concerned. Very interestingly, you will see material even like paper and cardboard, etc., over here, reasonably high strength and stiffness over there compared to foams and elastomers, but much lower compared to metals, alloys and composites that you see over there. Then there are a big class of natural materials as well, like wood and bones, etc. So those natural materials form one other cluster over there. And it's not like these are independent clusters. There's a lot of overlap. There could be natural materials which are as good as let's say a certain foam for a certain application. There's a kind of trade-off that you have. For leather, for example, is over here, etc. So this is kind of and ceramics. Again, two categories. We already talked about non-technical ceramics. There are also technical ceramics. And for example, the carbon-carbon kind of composite that I was talking about is essentially made out of those kinds of technical ceramics. Alumina is another example of such a thing. Al2O3, that is aluminum oxide, which is typically used in the form of particulate reinforcements in a lot of composites, right? Especially metal or metal matrix composites, right? Then polymers. Yes, polymers very important for us because we are going to study matrices, and one of the most common matrices, at least so far in the aerospace industry, are the polymers. And within polymers, of course, you have epoxy, etc. Another example is polyethylene, PE. There are composites which are made out of polyethylene fiber in a polyethylene matrix. They're used for travel, like suitcases and things like that. Some really lightweight suitcases which can be made out of PE kind of composite. So various possibilities are there. But this kind of a plot is not directly relevant for aerospace engineering applications because density has not been factored into it. Another thing is also we have not taken into account the elongation, percentage elongation. Sometimes you get 3D plots where you have on the third axis the elongation so that you can make a decision based on all three of them, and typically these two are divided by the density before they are plotted on this. So are there any questions on this plot before we move forward? Okay. So now we have answered this question as well over here. So what are composites? Some examples of composites, typical composites used in certain applications. Now we want to, within composites, we want to break this Y into two parts. We already saw Y composite itself, but Y fiber and Y matrix, these two we will start with, starting with the fiber, and then we will get on to the matrix, right? So why do we use fibers? Okay, so that's the question. And in order to be able to answer this question, we know that yes, fiber by itself, whose properties is what we have been listing so far. We have not listed any composite overall property, just fiber properties, which looked very, very attractive indeed. But we have been seeing most of them in the properties in a fiber form. So in order to be able to answer this question, we have to see that there are certain superior properties associated with the fiber material, right? So to be able to understand that, first of all, we should ask ourselves, what is meant by a material property? So what do you understand by a certain property being a material property? Given any property, would you call it a material property or not? What is the criteria for that? When do you call a particular property is a material property? When you say it's not a material property, yes.
It's a property that doesn't depend on your geometry.
Good, very good point. Yeah. Anybody else? Any addition to what Patrick said? So because we've been repeatedly saying that geometry and the material are the two options in designing a structure. So Patrick rightly pointed out that if it's a geometric property, it cannot be a material property. So that's kind of obvious. So there's not kind of an overlap. So anybody else, anything? So kind of agree with him. There's nothing to add, right? So let's go ahead and see. Okay. So now let's take, for example, the ultimate tensile strength as an example. Okay. Would you call it a material property or not? Or is it a geometric property? Huh? Yeah, looks kind of trivial or silly question for me to ask, right? But we will see it's not so silly after all, okay? So the ultimate tensile strength you typically give for a material in gigapascals, and the question that I'm asking is it a material property or a geometric property? And you seem to be kind of unanimous with the opinion that it is a material property, and by material property you said that it should not depend on the geometry, because otherwise it would be a geometric property, right? So the next thing is another question that I would like to ask you. Do the material properties depend only on the chosen material, as Patrick said, or on the shape and the size of the object as well? Because shape and size, remember, are geometric features, right? They are a kind of definition of the geometry, what kind of shape it is. It's circular or square or rectangular, etc. And again, in 3 dimensions is a cuboid or cube or a sphere, etc. And then the size of that, what's the diameter, or what's the length, what's the width, what's the height, etc. So do material properties depend only on the chosen material or on the shape and size of the object? Kind of a repeat question, probably rephrased in a different way. Would you like to stick to your same answer, or is there a change, or is there a modification you'd like to do? Yeah, Nilesh?
I feel like for like material properties, they can be influenced by like the size and shape of like the object. That like if it's like a really thin like material and like that material isn't supposed to be that thin, like the property of the material itself like might change like how it reacts to other like outside forces and stuff like that, you know. So I think it could depend on like the size and shape of the object.
Okay, very good point. Anybody agrees or disagrees with Nilesh? Or would you like to add to what she said? Anything? Yeah? No? Okay. So let's go further. Yeah, this is a very good point Nilesh brought out over there. Let's go to the next question over there. Okay. So in fact, she kind of touched upon this very example to substantiate her claim. Should the ultimate tensile strength, which is what we are talking about on the top, whether it's a material property or a geometric property, we are asking, should it depend on the fiber diameter? Fiber diameter, remember, in other words, we are sticking to a shape, so but we are trying to change the size, which is the diameter of that fiber in micrometers, let's say, and we keep on increasing or decreasing it, and to see, well, would the UTS depend on it? I think she had a say already on it. Anybody else would like to claim or counterclaim on that, or add to what she said in terms of this? Yes or no? First of all, yes, Alexandra.
Does it also influence what the way that
Yeah. So we will get into the woven fabric a little later, just like we will get into the composite a little later in terms of bringing in the matrix as well. Right now we are talking of an individual fiber, okay, just one fiber at a time. I'm taking a carbon fiber, I'm taking a glass fiber, or I'm taking within a carbon fiber various diameters of the carbon fiber. And as we already saw, within carbon fiber itself there are different companies which make it. Within each company there are many types that they make, some high modulus, some high tensile strength, etc. So, but we will stick to one type, one manufacturer, one type, but different diameters. Okay. So then, should the UTS depend on the fiber diameter? Anish.
I mean, like, could it be like kind of like the difference between like an intensive versus extensive property of the material as well? Like, I know, like, I remember we were talking about this, but could you like compare like would like material property be like a specific property? Like, it shouldn't be dependent on like the mass of the material, you know? Like, can it depend on like specific property and like specific strength and specific volume, you know, on that?
Right. So as the performance index, we already defined the specific strength, for example, as the UTS divided by the density, right? So, but we are going back to the absolute values here and saying that does the UTS itself depend on the geometry or not, right? So, because this is essentially, you all agreed that this is a material property, and Patrick already said that a material property should not depend on the geometry, it depends only on the material, doesn't depend on the shape and the size. Okay, but there seems to be a kind of a conflict there, right? So, yeah.
So isn't the ultimate tensile strength, it's a per area measurement, so in the fiber diameter, it's hard to
Yeah, a good point, but remember that the ultimate tensile strength when you're talking about, you're not talking of forces, you're talking of force per unit area, stress. Okay, so its unit is Newton per meter squared. right? So the gigapascal or your megapascals are essentially talking about pascals, which are nothing but a Newton per meter squared. So it's already per area, which is kind of built into it, right? See, if it had the same material property, that is UTS, the larger the cross section I take, the more load it should take. That becomes kind of obvious if the material property is not changing. So, but we are not getting there. We are only talking of the UTS itself, which is already a force per unit area and was the material property. We all are kind of unanimous about it. And we said that material property is something that depends on the material, not on the geometry, and shape and size are geometric features. And in this case, the thing that I am trying to vary is the size of the thing, and therefore it's a geometry that I am changing, and I am saying should the material property change. Patrick?
If the ultimate tensile strength is a material property, then it shouldn't matter what the diameter is.
Right. Good point. Yeah. None of you are wrong, by the way. You could have contradictions, conflicts, but none of these are wrong. Look from different perspectives, both are right. Okay. So we're just trying to blend these responses together to see what's really happening. Yeah. So let's probably go to another question. Things become a little clearer. Okay. Now let's have election time, voting for a trend. Okay. Because this is what the question that I asked in English. Now I'm putting it in a form of a graph, a mathematical response to that. Right. So on the vertical or y-axis, I have the ultimate tensile strength in gigapascals, and on the x-axis or horizontal axis, I'm having the fiber diameter in microns. Okay, but it could, if I keep on increasing, just like we had the log-log plots, for example, it can go from microns to millimeters to meters, etc. So it can have whatever it wants, right? But essentially, I'm trying to increase the fiber diameter. There, I'm trying to see what happens with the ultimate tensile strength. Now, what do you think the trend would be? First of all, one choice I would give you is monotonically increasing, by which we mean as we keep increasing the diameter, the ultimate tensile strength keeps on increasing. In a way, what Ariek said in terms of if you're looking at instead of UTS, instead of force, if you're looking at, what you say is right, that force will be UTS multiplied by the area, and as I keep increasing diameter, the cross-sectional area will increase, and therefore the ultimate tensile load, not the stress, will increase. So that could typically be the way it looks, right? Assuming that the material property doesn't change, right? But now what we are focusing on is not the load, not in newtons, but gigapascals, which is Newton per meter squared, which is a material property, no doubt about it. But this is a geometric feature. This is one choice. This is monotonic. Okay, let me give you all the choices, and then we'll probably look at it. The other option is that, as Patrick said, it's a material property. Give me a how is it going to change with the diameter, right? There's no way this is going to change with the diameter. It's a geometric property. That's a material property. These two don't go with each other, don't change with each other, and therefore it's a constant. That's another option. Okay. Third, the exact opposite of the A, which is monotonically decreasing. I keep increasing the fiber diameter, and the ultimate tensile strength comes down. Okay. So fourth choice, none of the above. Maybe some other kind of variation, which is neither monotonically increasing nor monotonically decreasing nor constant, but maybe some kind of a vary function, increasing, decreasing, maybe goes to a maximum value, comes down, or goes to a minimum value and then starts increasing again, something like that. Okay. So now, how many of you would think it is choice A? Nilesh, okay. I'll come to Y a little. You can think over that. Anybody wants to go with choice B? Patrick, Karyak, and Alexandra. Okay, so that means nobody choosing C and D. Not even you. Okay, so good. Let's since you are a unique choice, let me give you the floor first and say, why do you say it should increase? Why should the UTS increase with the fiber diameter?
I would just think that if there's like more of the fiber available, it would be harder for like it to Like, I don't know. I guess that's why I chose it. Yeah.
Okay. Okay, Patrick.
Still think the same. I think unless you change the material, you can't really change the tensile stress.
Yeah.
I think that can move back.
I thought you chose C, right? No, B? Okay, okay, I'm sorry. Yeah. All of you chose B? Okay. Okay. So you're saying it's constant, right? Because it's a material property, it should not change with the geometry, okay? She says it has to increase with the geometric property because she explained the reason for that. So you know that, right? So now let's go and see what actually happens, okay? So we chose between A, B, C and D, right? But what really happens is that this is the kind of trend, okay? So we will argue it out, we'll see, reason it out. If you do an experiment, this is what you will find, okay? So the ultimate tensile strength, even though it's a material property, will decrease with the fiber diameter. And remember, the whole question that we are motivated by is YF, Y fiber, right? So what is so special about the fiber geometry? What is so special about having it in the form factor of a fiber that makes it so good? These materials are not something unusual to us. We've been talking of glass, carbon, etc. Glass, carbon are available in bulk forms as well. They're not as strong as the kind of glass fibers we're talking about. We have the glass in the window over here, so it's not as strong or as stiff as the glass fiber. So what is so special about the glass fiber? This is also glass, that is also glass, right? So there's something about the fiber diameter or fiber geometry that makes it kind of special. Anything that you would like to add to your answers or maybe modify your answers now? Oh, of course, the answer I have given, so this is the true thing. So take it from me for now. I will explain why. Yeah, go ahead.
I mean, it's kind of like how, like, with windows and stuff like that, you have, like, glass in, like, very long, like, larger, like, sheets, right? But you wouldn't see that with, like, a fiber matrix. You'd see smaller glass, like, on that matrix with those.
Yeah,
like,
yeah,
right?
yeah,
And,
yeah.
like,
But let me just interrupt. Right now, we are still not gone into composites, so we're not talking of matrix at all. We are only talking about the fiber alone, only the glass.
Yeah,
Okay.
but like,
Yeah.
like you could probably see like just having one very long, very big like piece of glass, right? It's like easier to break, right? Like you can throw a ball at it, it's
Yeah,
going
yeah,
to break,
yeah,
you
yeah,
know?
yeah.
But like if you have multiple small little like glass pieces, you know, that's probably going to be harder to shatter because it's already very small.
Yeah,
you know?
good point. It's valid, but it's a different question that it answers, because what we are talking of is the ultimate tensile strength, where we gradually increase the tensile load and then see where it breaks, right? Whereas impact is an important application. It's there, shattering and how much energy it absorbs. So what you told is absolutely valid for that. But right now we are exploring why is this ultimate tensile strength, which means that I have this fiber on which I am applying a tension. I am going on increasing that tension, and at the point of failure, I want to see what is the value of the tension, what is the value of the cross-sectional area, divide the two, that is the ultimate tensile strength. That's what I get. Now I do the same experiment with a slightly larger fiber diameter and slightly larger fiber diameter. As I keep on increasing the fiber diameter, it's no longer a fiber. What does it become? Yeah? Bulk material. So you can say a rod. Okay, a rod, for example, is just a circular cross-section rod that it becomes, right? A glass rod is not known for its strength or stiffness so much as a glass fiber is, right? Similarly, a carbon rod is not known for its strength or stiffness as much as a carbon fiber is, right? So there is something specific that is happening when I get into this regime of the order of microns that I'm dealing with as a diameter. There's something special that is happening, which is having something which is not changing so much rapidly. If you look at this region, for example, it is increasing as I decrease the fiber diameter, but by not a big margin. But once I go closer to this end, you see a steeper increase. Yes, Ajay.
Since the ultimate tensile strength is load divided by the cross-sectional area, cross-sectional area has diameter squared term.
Mm-hmm.
And so that kind of explains the behavior because if you hold the load at a constant, if you want to over the diameter squared, which is kind of similar to the behavior.
Yes and no, because the load capability of a structure is maximum load carrying capability of a structure, especially let's say a rod or something like that, is dependent on both the material and the geometry. Okay, so as long as I have the same material and its material property doesn't change, like for example I take two points over here, okay, it's almost horizontal over here, right? So this has larger diameter, this has a smaller diameter. Now this will actually take much more load in terms of newtons, but they take almost the same as far as Newton per meter square the stress is concerned. So the stress is what is a material property. Okay, the stress at which it fails is a material property, which is what we are calling as the ultimate tensile strength, UTS, right? But the load itself is not a material property. It is a combination of a material property and a geometric property. Cross-sectional area times the ultimate tensile strength becomes the load of failure, right? So, when you are dealing with this almost constant, here what Patrick said earlier is really valid, that it's a geometry, it's a material property, it should not vary with geometry, and therefore his answer was absolutely right beyond a certain level, right? So it's not that it's wrong, it's a certain region where his answer is valid, but there's also a certain region where his answer goes absolutely wrong and somebody else's becomes better, right? So what is actually happening here? Yes, Patrick. Yeah.
Because as you like decrease the amount of the material, you start to like lose some of the properties because you're just looking at molecules instead of like the overall material itself.
Beautiful. Yeah, you're getting towards the right kind of answer, right? In fact, there's one more question I'll be asking towards this end where your answer is almost right on trot. Okay, but even before we get to that end, which is where you're talking of such orders of diameters that it's of the order of microns, etc. Molecules or atoms, etc. Even before we get to that, which is many times a molecule size or many times an atom size, this is already having a steep slope. Okay, so what could be the reason here? The reason that you mentioned is very much valid, very close over here. So that's the reason why a huge steep increase. So somewhere in between, you see, it's not as horizontal as here. There is a certain slope, and here I'm not giving you actual numerical values here because it varies from material to material, though here I'm specifically looking at glass fibers, but the trend is similar with any fiber that you take. So, but what I'm saying is that, take it from me, that these fiber diameters in this range, for example, is way above the diameters at the atomic or molecular level, and still it happens that as I decrease the fiber diameter, it tends to increase the tensile strength, which is ultimate tensile strength, which is a material property. So what could be happening there? For this, we need to understand a little bit of what is happening at the ultimate stress value. It's breaking, right? How does it break? There has to be something that is giving up for it to break, right? And we are not even talking about molecules and atoms at this stage. We're still at fairly continuum levels. So what is actually happening? Why is the material giving up? For the material to give up, because we say ultimate tensile strength, the entire thing has to break. So in other words, there's no longer contact between the top portion of the specimen and the bottom portion of the specimen. That's completely detached from each other, right? But for that to have happened, there has to be some kind of an initiation, right? It should have initiated as a small crack, a micro crack, and then it starts slowly growing because the stress is so large that it's not able to handle it anymore. That crack starts becoming bigger and bigger. Eventually the whole thing gives way, right? So what can you say about that initiation as far as a thinner fiber and a slightly thicker fiber is concerned? Because the initiation has to have some kind of a causation, and that causation is typically some kind of an imperfection with the material itself. the way it's manufactured or the way it is put into a particular form or into a specimen, etc. So essentially you are having some kind of imperfection that is there within the fiber itself, and most of these are surface level issues, right? Now, how much of a surface does a smaller diameter fiber have compared to a larger diameter fiber? All that you have to look at is the circumference 2 pi r divided by pi r squared, which is the area. So you're looking at 1 by r over there, okay? So what we are talking about is an imperfection density on the surface. So that imperfection density becomes lesser and lesser as you go to smaller and smaller fibers, okay? For the same amount of fiber, you are getting lesser amount of damages which are already present, surface level. So then what happens is that it's much more difficult for it to initiate first of all and then fail. Whereas here it becomes a little more easier for it to fail because there are many more micro cracks that are already there on the surface, okay? So let's take this. So here I've started giving numbers a little bit over here. So the fiber diameter, let's say, goes from in this range 10 microns to all the way to 100 microns. Still the maximum I'm talking about is just a 0.1 mm, okay? Very, very small indeed, right? But this is more typical of fibers that you would see which are typically used, whether it's glass fiber or carbon fiber. Typically of the order of 10 microns is the diameter that are used, especially in aerospace applications, many other applications as well. Now we bring in what Patrick said in terms of what happens at that other end. Does it go on increasing forever? So that monotonically decreasing doesn't work, right? So there are end conditions where here we saw it's kind of becoming asymptotic to something. It become almost horizontal. So it's extrapolating to what Chinababu was mentioning as the bulk strength, okay? So it's essentially becoming that glass material's bulk strength, like the kind of glass we use for the window panes, etc. on ordinary normal windows, not the windows on an aircraft, which are typically laminated and more higher quality. So here we're talking of extrapolating to the bulk strength. And what is that typically of the order of? You see, 0.17 gigapascals. And what is Patrick's value there at the atomic or molecular level? 11. So you see the huge ratio of 11 by 0.17. It's almost 100 times, right? So that is the kind of ratio that we are looking at. And what is that? So it doesn't increase forever, keep on decreasing the diameter. Obviously you can't keep on decreasing. You reach the level of a molecule size or an atom size, you can't reduce it beyond that, right? So then it extrapolates in this case to the cohesive strength. So cohesive strength is essentially between two atoms or two molecules. What is the chemical bonding strength that you have? So it is extrapolating to that, and for glass it happens to be, for adjacent layers of atoms, it happens to be approximately 11 gigapascals, right? But typically if you go back and look at the tables that we were looking at in terms of the glass fiber properties, it was not as high as 11 gigapascals we were giving for UTS, of the order of 4 gigapascals or so. So which is essentially fiber geometries. This is the kind range that we will typically be using in many aerospace applications and a few other applications as well. The fiber geometries, why is it so special? Why is it doing so great? Because it harnesses much larger increase in ultimate tensile strength and the Young's modulus for any given material. So we are plotting all these things are for glass, but starting all the way from bulk glass and going to tinier and tinier diameter fibers, and we are eventually reaching the atomic levels where the cohesive strength is what kind of dominates at that end. So now, as I said, this is a trend that I have plotted for a specific material, glass, but the overall trend, the actual numbers will vary, but the actual trend remains the same whether you plot for carbon fiber, even if I change from ultimate tensile strength to Young's modulus or a few other properties, you will see that it's almost a similar trend that you would have, right? So apparent reason for, in this case, especially in the case of glass, is the lower probability, as I said, of the failure inducing surface cracks, because those are going to initiate on the surface of the fiber. There are going to be a few micro cracks, and that is what is going to start growing and eventually make the whole specimen or the whole fiber break, right? Surface cracks generate and typically are generated during the fabrication of the fiber or handling it also before you put it onto a UTS machine, a UTM, in order to do the testing. So fabrication and handling induce these kinds of cracks, but they will be lesser in density for a smaller diameter fiber compared to a larger diameter fiber, right? So now that is answered. So now we go on to the second major constituent of the composites, that is the M. So we want to look at what is the reason why we are using a matrix. Any takes on that? Oops. Why matrices? Yeah, Nilesh.
You kind of need something that holds everything together. Because, like, fibers itself are very small and tiny.
Yeah.
So there needs to be like some cohesion between
Good.
all of the fibers. So the matrix is that.
Absolutely, yeah, valid point, but that's not the only reason. Any more reasons? Why fiber? We saw, because the tinier the fiber diameter, which is what, when we call it fiber, otherwise we would be calling it rods, is that it has less surface cracks, and therefore chances of it breaking are much lesser, and therefore it has large strength. So it's offering large strength, large stiffness. So there's all those hunky-dory properties that we saw for composites are predominantly coming from the fiber. But as Nilesh pointed out, we can't just have fibers hanging around loosely. We need the matrix for a certain reason. Are there any other reasons? Yeah, Alexandra.
I guess it also makes it more stronger in both directions. It's really together. It's not just if you have a fiber going this way and pull it, it would be stronger if you pull it sideways and not necessarily.
Excellent point. Yeah, yeah. So all the properties that we have been talking about, as Alexandra rightly pointed out, are properties along the fiber direction. Very superior, good strength, good stiffness, but you just try to pull it the other way around, gives up almost easily, right? So there is something weak about the transverse direction, right? There is also something weak about shear. If I try to apply a shear, one fiber slides over the other, and it's very easy to slide them over each other, right? Even if I have a bunch of fibers and I try to pull them this way and this way, it will easily give up, right? So shear in any direction, it's not able to handle. Like Alexandra pointed out, transverse forces and transverse stresses, it will not be able to handle either. Nilesh pointed out that we need to have some kind of a cohesion to put all the fibers together. Anybody else? Any answers? Any other reasons? Those are absolutely right reasons, but there could be other reasons as well. Okay, so let's start looking at some of them. It's an example of a matrix over there. So we'll try to answer some of these questions, and in the same slide we'll also try to take a look at certain examples of matrices after answering this question, right? So the first thing you already mentioned is to overcome the disadvantages of using only the fibers. So that's where you came from. You said, yes, fiber geometry is great. It offers a lot of ultimate tensile strength, etc. Even the Young's modulus, but in only one direction, right? So there is therefore a disadvantage with fibers. So whenever you are trying to bring a partner to a particular element that is already present in the system, obviously that partner is going to add certain value to the system as a whole, which is what we want, which means what is the existing element of that system is not able to fulfill that function. The new element is able to fulfill that function. So we are coming from a negative reasoning over here. There are certain things that are problematic with fibers, the cons of the fibers, which means that when you're taking only fiber, you can't do certain things, which once the matrix comes in, you will be able to do. So what are they? First is, as you already pointed out, one is transverse and the other is shear that I mentioned, but the third is longitudinal compression. See, even in the direction of the fiber, it's good only in tension. Even in the same direction, if I compress it, it's just going to collapse, right? So fiber by itself, if it is there, it's just going to collapse. So not only is it bad in transverse direction stresses, not only is it bad in shear in all directions, but even in the longitudinal direction, in which it was very good at tension, but in compression, it's really poor, right? So it cannot support longitudinal compression, and therefore one of the main loads in the case of aircraft structural components, which is bending, cannot be supported, because bending involves both tension and compression. So if, for example, if I take this structure and try to bend it, it's very clear that the bottom portion is going to stretch out, it's going to be under tension, but the top portion is going to be pressed in, pushed in, it's going to be under compressions, right? So whenever there's a bending load, even with a pure moment, you can very easily see that part, typically half the cross section is under compression, half the cross section is under tension, loosely speaking, and therefore an inability, if you have a bunch of fibers and try to bend them, obviously it's just going to collapse. As much as it is going to collapse by compressing it, by shearing it, by transversely pulling it or pushing it, same way in the case of the longitudinal direction, which is like its ultimate property as far as tension is concerned, you just reverse the direction of the load, compression, and it's going to give up very easily. So it has very poor longitudinal compression properties and therefore bending properties, and also it has very poor transverse properties, as Alexandra already pointed out, right? So the second reason is what Nilesh already mentioned, is to hold the fibers together in a structural unit. Otherwise they are like a bunch of things, they are good by themselves, but as a unit together they are not going to serve any purpose. So you really need to hold them together, which is what the matrix does, one of the things that the matrix does, right? This third thing, and this is very beautifully brought out by the typical textbook that is used in Georgia Tech for this course, Bauschow and Craig, is in terms of distributing and transferring the stresses. In other words, you're going to have certain load, and that load has to be transferred to the adjacent materials, the partners in crime. So what is happening over there? So you have a fiber, you try to pull it, and then let's say you typically have a set of fibers over here, and let's say they're all within a matrix, and I'm trying to apply a tensile load, let's say, over here, right? Now, what would happen, for example, if let's say one of the fibers were to break over here, right? No material is lost, of course, it's just giving up, right? It's trying to stretch. Other fibers are all intact. Now what happens to this? While all the fibers were fine, they were all sharing the load, right? So now one of the fibers has given up. So what do you think would happen? Yeah, Nilesh.
The other fibers would like not like the load that like smaller that the fibers didn't.
Other fibers will share that, whatever that was doing. Is that what you're saying? Yeah, that's true. But what about the portion of the fiber which still remains? Is it useless? The broken fiber, once it's broken, is it kind of useless? Do the other fibers have to do all of the work in terms of taking the load, or does this also still do some work? If at all it does, is it significant or negligible?
I think it would still do work, right? Like it would still do work. It's not like useless. It
Yeah.
still takes up that area. It's still good. Has
Right.
its own properties,
Right,
you
right.
know? Like it just that one specific part that broke off, you know, like that might not be able to carry it
Mhm.
because it's broken. But
Yeah.
all that.
Yeah, how much of that load, like let's say for example it was taking, each fiber was taking about, let's say 10 megapascal stress earlier, okay? Would it continue to take 10 megapascals or maybe fall to 1 megapascal, or would the fall be just to 9 megapascals?
So we have to take the 10 because like the material, like it's not just material, you know, like it's still
Yeah. Yeah, your answer is right, but why?
I mean, like because it's like
Even though it's broken, it's still able to take almost 10, you're saying, right? It was originally taking 10, it continues to take almost 10 megapascals, even that broken fiber after breaking, right? So except for this region, okay, that's fair enough. But that's a very small region, and rest of it you're saying is taking almost the same as it was taking before. Absolutely right answer, but I need the reasoning for that.
It's like the matrix is still like holding like that place together, you know? So like it's not that like the fiber is disappearing, it's still there, you know? It still would be able to hold on to like it would still be able to handle that load that it's giving. It's just that one part of the fiber that's broken, it wouldn't be able to handle that it's broken. But like all the other like the other material exists, you know. So I don't see why it wouldn't
Yeah,
be.
yeah, it's a good point. What Nilesh is saying is that, suppose, rephrasing what she's saying, if there were no matrix and then this had broken, then I was trying to pull this bunch of fibers, only the unbroken fibers will take the load. But now I not only have these fibers and a broken fiber, but also I have a matrix, right? So the matrix is doing more than one function, mind you, okay? And one of the functions that we are focusing on right now is to distribute and transfer the stresses, the loads, right? So what's happening is that this is not an isolated broken fiber. This is in some way joined to the other fibers through the matrix. In between there is a matrix, right? So when this kind of a break happens, yes, the boundary condition at this place will suggest that the normal stress at that broken end and this broken end is 0, right? So I was saying it's about, let's say, 10 megapascals to start with everywhere, all the fibers. Now it, as Nilesh rightly pointed out, it will remain 10 megapascals, but it will become 0 over there. But within the order of a few fiber diameters, which is of the order of a few microns, remember, it will pick up, and as she rightly pointed out, it will be 10 megapascals. So in other words, the amount of fiber that we are really losing out on in terms of functionality is almost negligible, and it works in fact, in reality, all fiber reinforced composites will have many such breaks at many different locations in a normal situation, and it's a healthy composite. Absolutely no issues, because the matrix is going to transfer that load. How does it do that? The fiber is very good, remember, at tension. What is the matrix good at? It is good at shear. Okay, so it's able to handle a large shearing stress. So if I apply a shearing stress like this, trying to pull it apart within the matrix, you see here, it's able to handle quite a bit of shearing stress, whereas two fibers cannot do that. The matrix is offering that shearing capability, and what is happening at close to this is that where it breaks, it takes much more shear stress and immediately transfers the load to the rest of the fiber, the rest of the broken fiber, as well as the adjacent healthy fibers. So that way, what's going to happen is that this is going to be really good at handling things. But the breaks that I have purposely marked here on all the fibers, that here I put it at different locations. If all of them were broken at the same length from the top or the bottom, then you have a weak link over here that can break, because that's just pure matrix. All the fibers are broken at the same distance from the bottom or same distance from the top, then you can have it catastrophically failing, right? But that's a very, very rare situation. It's a statistical thing that typically the cuts or breaks in the individual fibers, because these are fairly long structures that we'll be dealing with, and you may not have fibers running through the length. Typical fiber lengths will be much shorter compared to the overall length of most structure panels, spars and stringers, etc. So, but the cuts will typically be at different locations, and very soon the matrix will transfer that. And beautiful, simple but beautiful mathematical model for this is given in Bauscher and Craig's book, beyond the scope of this particular course, but those of you like differential equations, solutions to differential equations, or applications to these kinds of problems, you can try to take a look, search for that and try to take a look on stress transfer in matrices. So distribute and transfer stresses is what this typically does. So there you can prove that within the order of a few fiber diameters, few microns, that is, it will get to the full strength, that is, the whatever it was taking earlier, it will continue to take. So that's the beauty of it. So that's another advantage of having the matrix over here, right? So next, we are not done with what all the matrix does. It's quite effective in terms of its multifunctionality. So the other is, again Nilesh pointed out, is to protect the fibers from external damage and the environment. The environment could get very hot, it could get let's say humid, it could get corrosive, but the matrix will protect the fiber from all of that, because remember that the fibers are embedded within the matrix, and therefore except for a few which lie probably on the surface or just parts of which come out to the surface, except for that most of the fibers are contained within the matrix, and they are all protected from both loads, mechanical loads, as well as environmental conditions like temperature, pressure, humidity, etc. The next thing is, depending on the kind of matrix, remember so far most of what we said was valid for all matrices, but there are certain things which are valid only for a metal matrix, or only for a ceramic matrix, or only for a polymer matrix. There's one such thing I want to introduce here. If it's a metal matrix, for example, you could have boron fibers in an aluminum matrix, then the metal matrix can provide ductility. That is essentially the ability to draw it into wires or make it into certain different shapes. In other words, the elongations are pretty good. But plastic matrices are notorious with this. They are brittle. But if you have other kinds of matrices, like especially metal matrices, then you can have that advantage. With ceramic matrix also it doesn't work. So there also ductility is not something that is provided. There could be certain matrices which could provide greater toughness, which is more stress strain, more area under the stress strain curve, and therefore ability to absorb the energy. So toughness, again another material property. Some materials like polymer matrices, for example, can offer electrical insulation or thermal insulation even, because polymers are very bad conductors. Therefore you could utilize them in certain applications where that's of importance, right? So those are some of the major contributions of a matrix that you ought to remember. Purely from a structural point of view, they offer transverse strength, they offer compressive strength, even the longitudinal direction, they offer shear strength. And because they offer compressive strength, they offer bending strength as well, or they are partners in that. The tensile portion of that is taken care of pretty much by the fibers. Okay, now let's look at the various types of matrix materials choices that we have, more in terms of families of matrices, and we've been talking about this in a haphazard way here and there. We try to put them together. So what is the basis of a choice of a matrix? Typically the fiber material is chosen first in any application, because that's the costlier material usually speaking, and you typically want to choose the best available fiber for a particular application, as long as it is within other constraints like economical constraint. You are able to afford it, you're able to purchase it in large enough quantities, not only for the aircraft that you're making, maybe maintenance, repair, and overall later on you should have a continuous supply. You should have multiple suppliers, because if one supplier fails or goes bankrupt, can somebody else supply that material for you? So all these non-technical considerations are also taken into account in arriving at a decision on what fiber you have chosen. Now you have chosen a fiber for a particular structural component, let's say a spar or a spar cap, let us say, right? Now you want to see what matrix goes with that. First, most important thing is the compatibility, physical compatibility, chemical compatibility, thermal compatibility. All kinds of compatibilities have to be checked. Otherwise, it can go quite awry in terms of how these two work together as partners, right? And apart from compatibility, the second most important criteria is that structural component which is going to be designed with this matrix. Where is it going to go? What kind of loads are dominant there? So based on that, you can make certain choices in terms of that. So there, the service temperature or the thermal environment becomes the most critical, because there's a huge range of difference between how a polymer matrix behaves, what kind of temperatures it can take, to what a metal matrix or a ceramic matrix or a carbon matrix can take. So based on that, we have choices that are made. So, and also these are typically in an increasing order of cost mostly, but there can be outliers in all of them. So the first thing is, within polymers, one category is thermosets. okay, which have been used almost dominantly for a long period of time, and these typically can take up to 150 degrees centigrade. As I said, there can be many outliers. There could be quite a few thermoset polymers which can go beyond this as well. So don't take these values as sacrosanct. There are variations possible, but this is kind of a thumb rule with which we will work. So some examples of such thermoset polymers are epoxy, which is almost ubiquitous within the aerospace industry, but also polyesters, right? Then the second is also polymers, but what is kind of catching up today, as I mentioned in one of the previous classes, is the thermoplastic polymer, which is having an ability to be recycled, but also it has typically larger temperature capabilities. But there are certain thermoplastics, mind you, which have lower temperature capabilities than even the thermosets. So I'm typically talking about the examples that I'm giving there. So those are typically able to handle slightly higher temperatures, which might be required for certain applications of the aerospace structural component. Okay. The third is when you go to even higher temperatures, what do you do? None of the polymer matrices will suffice for such applications. You will have to go for metal matrices like aluminum matrix, etc. And those, again, depending on the specific metal, can go up to a fairly large temperature, which are again still much lower than their melting temperatures, but they can take fairly large temperatures compared to polymers, about 1250 degrees centigrade, right? Next, if you have even higher temperatures, what do you do? Go from metal matrices to ceramic matrices, right? Ceramic matrices can take all the way up to 1650 degrees centigrade. So some examples of that are borosilicate glass, and then if you have some kind of re-entry vehicles which are coming back from space where there's a huge amount of aerodynamic heating, for example, then you might even need active cooling systems which are kind of continuously cooling the material. In addition, you will need high performance materials, high temperature capability materials, and one such thing is carbon matrix, usually used with a carbon fiber because the compatibility is pretty good over there. So this is one of the primary criteria, the service temperature, based on which you choose a matrix which goes along with the fiber, but even before that you have to check for various physical and chemical compatibilities, right? So that's as far as the why question is, what is answered. Now we're going to where. Okay, so where some of these are used, and I would not take too much time on this because you've already given examples to me of in certain Indian aerospace applications where all these have been applied. So we will just take some random examples and we will move on to the most important question of how, right? So these are examples all the way from space to aeronautics to missiles and rockets and other kinds of aircraft, etc. So you see different examples over here. So you see them in not only aerospace structures like rockets, missiles and satellites, where to a large extent the E by rho or square root of E by rho criteria of the stiffness based design will be dominant. Not that the other criteria are not important, just that that will be the most important criteria in terms of weightages you're going to give for all the three criteria put together. Then next is helicopters and airplanes. Then we come further down to the ground for typically automobiles, some of the high-end structures which go into, let's say, F1 car racing cars, and or even yachts and ships which are of high performance category, or aircraft carriers, for example. Then wind turbine blades, so typically for green energy, where you're trying to tap into wind energy. So many of these turbine blades are massive structures running into tens of meters, very, very long structures, and they could become very heavy if they are made out of metals or typical high density materials, which are still strong and stiff, but it might be too much of a load, especially for the pole, and especially when the winds become very large, it can become disastrous. So many of the wind turbine blades are made out of composites, and Bangalore is lucky to have a lot of these manufacturers of wind turbine blades. That's why if you go to highways around Bangalore, you will see more often than not many of these wind turbine blades being transported from one location to another where it's utilized within India or even exported, because many of the Danish companies which are very good at this particular kind of energy, wind energy, have a lot of their research facilities as well as manufacturing facilities for wind turbine blades made out of composites here in Bangalore. Offshore structures. Now, these are, let's say, for example, oil pipelines running for hundreds of kilometers from a particular place where oil is being tapped all the way to the shores where you're trying to extract the oil. And many of these applications, composites are being almost routinely used because of the primary reason that the metallic pipes that used to be used for a long period of time are not capable of handling such large range of temperatures through various seasons, and also the corrosive environment of the sea water, salty water, and therefore composites become a very good candidate there. They can take a much larger range of temperatures underwater, and also can resist corrosion much better. So many offshore structures, even some cases, even if these are made out of one material, the joints could be made out of a different material because based on requirements, because as I said, these run for hundreds of kilometers. They may not be made as a single piece. They might have to be joined at various locations, and you might have to give room for thermal expansions, etc. So these joints are fairly complex structures. They're not like ordinary joints of one pipe going into the other being welded or something like that. It's much more complex to allow for some movement, but at the same time it's oil proof so that the oil doesn't leak. So then there are containers, piping. So again, shipping containers, for example, these are massive structures, very heavy. So if they can be made out of composites, they can probably take much more cargo with them, so which is much more payload. So for the operators of ships and shipping companies, this becomes really lucrative if you are making containers out of composites. Initial cost will of course be large, but the overall you'll be trying to maximizing your income, and therefore it will easily pay off for the extra initial cost quite quickly. And piping I already mentioned. In addition, you have sporting goods, which also we already talked about earlier. Very interesting, a lot of electronic products, especially printed circuit boards, PCBs, etc., are made out of composites as well. Again, they have specific advantages. E-glass, for example, electric glass that we talked about, has certain electrical properties which could be tapped into by using them for electronic applications. Similarly, electrical appliances as well, typically high performance electrical appliances could be using them as well. Now let's come to specific aerospace applications. One example which is kind of very peculiar to aerospace and in particular to helicopters is the usage of anti-symmetric laminates. Okay, so you say a laminate is symmetric if about the mid surface you have the same set of angles. Let's say if I have theta 1, theta 2, theta 3 on the top above the mid surface, at the bottom also I have theta 1, theta 2, theta 3 at the same distance as the top layers. But now, if wherever I have theta 1 on the top, if I have a minus theta 1 on the bottom, if I have a minus theta 2 on the top, I have a plus theta 2 at the bottom, etc. So in other words, the angles are the same in magnitude but opposite in sign. Then you have what is known as an anti-symmetric layer. Okay, this is very rarely used even in the aerospace industry, but one classic example where it's been kind of a godsend is where you have helicopter rotor blades where you want extension twist coupling. In other words, already there is an extension load because of the centrifugal forces, and the pilot is applying the twists and essentially the control of the helicopter, which direction it has to move, is happening because of that, as we discussed in a previous class. So therefore the extension and twist coupling is very important. How it used to be done earlier is just by manufacturing the blade itself with a small pre-twist. But now we can not only do that, but we can also use composites in an anti-symmetric layup, which is kind of a pseudo way of introducing a pre-twist. So you can have the best of ways from both of these possibilities. One is anti-symmetric layup, another is a pre-twist, from a geometry point of view. So let's see an example, some examples of where it is used, right? So the tilt rotor V22 Osprey that you'll all be familiar with, the Bell helicopters, there is a classic case of where it is used. So here you have a situation where there is extension twist coupling, and antisymmetric laminates can do the same thing that a pre-twisted rotor blade can do. And as you see, this is a tilt rotor where part of the time it's operating like a helicopter when the rotor's shaft is vertical, and when it is horizontal it's flying like an aircraft as if it's a turboprop kind of an engine, right? So in both cases different values of this pre-twist would be probably important, and to have that kind of a wide range covered, it's always good to have not only pre-twist but also anti-symmetric laminates, so that as a combination they do a much better job. So you see them used in such helicopter flex beams, you use them in aircraft propellers, whether it's a turboprop or a piston prop, smaller aircraft which are still made out of reciprocating engines as the main propulsion element, or in this case which is a short takeoff and landing or a vertical takeoff and landing tilt rotor kind of an application, the V22 Osprey. And one example that you already covered when you were talking about, but let me give a little more detail of that, is in the Dhruv, or the Advanced Light Helicopter, which is nicknamed as Dhruv. Its tail rotor flex beam. As I said, there was a fatal accident of one of the prototypes, the pilot died, and we worked on a real-time health monitoring system for that. And you will see one of these specimens, one of these actual tail rotors in my office if you happen to walk by one of the days. So here you will see utilization of multiple composite materials. There's many of the materials that we talked about today as well, like the foam, for example, in between to create a sandwich structure. The top and the bottom typically glass fiber, epoxy composite, and as it goes down it is going to drop a few plies and it's going to become thinner and therefore almost like a pseudo hinge. And then, unlike the earlier fully articulated helicopters which used to have an actual hinge, so this doesn't have an actual hinge but a thinner cross section for some location, which gives very low bending stiffness and therefore much more flexibility. And then as you go closer to the root where it is attached to the hub of the helicopter, the loads or stresses are the maximum, and there you can't do with glass fibers, so you introduce carbon fibers. In fact, there's a hybrid composite of both glass fibers and carbon fibers over here, and you can very clearly distinctly see the difference because carbon fibers are darker in color and the glass fibers are typically yellowish golden color, and therefore you can, even with your bare, naked eyes, you can actually see where the carbon fibers are and where the glass fibers are. Okay, so this is just a picture of that, a cross-sectional picture. Is what I was talking about. The glass fibers you see in golden yellow and the carbon fibers in black on either side. Why are the carbon fibers on top and bottom and the glass fibers in between? Anybody? Why can't it be the other way around is what I'm asking. Yeah? Due to bending. Yeah. Good, yeah. So what he's saying is that the maximum load coming here apart from tension is bending, and when you have bending, we discussed already the triple functionality of all structural elements. One of them was essentially the ability to take more load comes when you put the material farther away, right? The more capable material should be farther away, because that's where it's going to contribute to a larger amount of bending stiffness, okay? And between glass fiber and carbon fiber, you've been seeing the numbers. Carbon fiber is a better material, stiffer material, stronger material, and therefore you're putting that on the outer portions where the stresses are larger, okay? And where the stresses are lower, you could have even done probably with foam or something like that, like in a sandwich construction, but here you're putting glass fibers so that they can take substantial amount of transverse shear, which is what is dominant in the middle portion, closer to what we call as the neutral axis or neutral plane, okay? And another interesting reason why this picture is something I have on my slide is in terms of the thickness. You start with a very large thickness close to the root, and then you start coming down to a lower thickness. The idea is that you want to have, where the stresses are large, you want to have more number of layers, more of carbon that you see over there, and then you see one by one these plies are dropped. In fact, we call these ply drops. So this ply, black ply, for example, the carbon fiber layer is dropped over here, and just glass alone over here. Then you see one more here, there is a jump over here. So these might look like discontinuities, drastic discontinuities, very discrete, but overall thickness, because the outer layers are not dropped, it kind of remains smooth in terms of the thickness, how it changes. And also, as soon as something is dropped, one ply is dropped, you don't immediately have a sudden change in the thickness. You will have a resin rich layer which will kind of taper down, so that it will gradually become one layer less thick, right? So similarly, you see some of the glass fibers and the carbon fiber layers are being dropped to reach to the thickness levels which are sufficient at the outboard, closer to the tip of the rotor blade. Okay, so then just to give you an idea of the kind of newer materials that we typically use, for example, structural health monitoring, etc., used for example for this particular application the piezo fiber composites, where each fiber is a piezoelectric material. It has a coupling between the mechanical and electrical fields, and therefore you can apply an electric field in order to change the mechanical properties, or you can apply the mechanical loads which are anyway coming from the rotor blade in its operation as a helicopter, and that kind of can be used as a sensor, because it will generate certain electrical signals, and those electrical signals will initially be monitored for the healthy structure, and once there is damage, it will be calibrated for that as well. And so once there is a damage, there is going to be a change in the signal, and the pilot can get almost real-time information in terms of the existence of damage, because the sensitivity of these are amongst the highest. And so how do we go about doing that? We take that extension twist coupling to the extent possible. We were talking of antisymmetric layups, and the best antisymmetric combination for this is to have plus 45 and minus 45 at equidistance from the mid surface, and then you have the maximum coupling between extension and twist in a mechanical sense, but the same thing holds in a piezoelectric sense as well, in terms of the sensitivity of a sensor, piezoelectric sensor, or the actuating authority of an actuator, and all of that was typically done by using this kind of a solution. Okay, so let me see. Yeah, maybe I'll just go through one slide of this and then we will stop, right? So this is a new topic, most of which we will cover in the next class, and in fact pretty much the rest of the course, where we are getting into the how part of it, which is essentially carrying out the structural analysis itself, right? So how to model typical flight vehicle structures, which I am abbreviating as FVS, flight vehicle structures, including of course composite structures. So I am not going to deal with composite separately and metal separately. We will derive a generic form for both of them, and then treat that as a special case. Okay. So how do we model flight vehicle structures, and particularly how do we model composite structures, because then metals can be taken as a special case of that, at least as long as failure hasn't happened, because once failure happens, the metals behave very strangely because of the elastoplastic behavior and plastic behaviors that can set in. Okay. So now there's a conventional process through which you model this. Is a traditional modeling procedure, and it's a 3-step procedure. Okay. So I'll just give the names of these 3 procedures, and then we will go into the details of that in the next class. Okay. So the first, so as I said, there are 3 sequential levels. One is at very low length scales, one is at the largest length scale, and one is in an in-between length scale. So it's essentially in terms of length scales that they're different, 3 sequential levels for mechanics of whether you're doing an analysis of structure or a design of a structure. This is typically how you will go about doing it. So the largest length scale, what you see on the rightmost over here, is what we call as macro mechanics, and this macro mechanics is done typically for both metallic and composite structures because it's at the structural component level. This could be a spar, this could be a stringer, it could be a rib, it could be bulkhead, it could be a skin, whatever, a skin panel, let's say, or something like that. So sometimes for smaller aircraft you could analyze the whole wing as a cantilever or the whole stabilizer as a cantilever. So that is also a possibility. So that macro mechanics or the structural component level is something that is done on a routine basis even for metallic structure, nothing new or special for composite structures. On the other hand, it's only material scientists who work with the case of micromechanics where you're getting into very small length scales for metals. So metals typically at the crystal structure. What is the crystal structure of the metal? That can have a lot of implications in terms of the overall behavior of the material properties and the different metals that go into an alloy can cause that. But typically we application engineers like in aerospace or automobile engineering, etc., we do not care for that in metals, but in composites we do have to care for that at the fiber level, at the matrix level, where we have to look at what are known as unit cells or representative volume elements, which have to be analyzed in order to get an equivalent homogenized model so that you don't need to deal with fibers and matrices separately as individual materials. You kind of come up with an artificial fictitious material which is having the same property as this fiber and matrix combination would. So that's essentially what we get into, and in between these two is what we have as the mesomechanics, the bridge between the large structural component of the spar on the one hand and the material level at the other end. How do you put them together? So that's your mesomechanics. So from the next class onwards, we will try to go into each one of these steps in a little more detail to understand the overall structural analysis procedure. Thank you.